Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. NRIS is collaboration between Sigma 2 and the universities of Bergen, Oslo, Tromsø, and NTNU to provide national supercomputing and data storage services. These services are operated by NRIS and coordinated and managed by Sigma 2. In this video, we will explore the new Olivia Linux cluster using the Cray module system. Specifically, we will use the triple nested loop to perform matrix multiplication, leveraging OpenMP for parallel computing. In videos 42, 43, and 44, we used the Cray Fortran compiler loaded through the Cray module system. In videos 45 and 46, we switched to the Intel Fortran compiler loaded through the NRIS module system. We will once again use the Intel Fortran compiler in this video, but this time it will be loaded through the Cray module system. We will also do a scaling analysis. This analysis involves measuring computation times while varying the number of threads, starting with a single thread and scaling up to 256 threads. Scaling analysis is a technique in parallel computing used to assess how effectively a system performs as more processing units are added. It helps identify whether increasing computational resources leads to performance improvements and to what extent. This process is vital for optimizing parallel systems and ensuring resources are utilized efficiently. I am already logged into Olivia and currently inside the MXM OpenMP folder. I can use the module list command to verify that my default home environment uses modules from the Cray module system. Before proceeding, I will clear the terminal. I will first list the contents of my folder. I have created a folder called Cray Intel, which I will be using in this video. Let's move into this folder with the cd command. Before examining the Fortran program that performs matrix multiplication, I will clear the terminal. I will first list the contents of my folder. We will begin by examining the Fortran program that performs matrix multiplication using the triple nested loop. I will open the program with the Emacs editor. I will use a matrix dimension of 32,768, and this Fortran program was previously reviewed in videos 41 and 42. I am using allocatable matrices in this program. The reason for using allocatable matrices was explained in video 42. I will exit the Emacs editor and return to the terminal. Let us take a look at the job script used to execute the Fortran program. The script is largely similar to the job script discussed in video 41, but in this case, I am using the Cray Intel programming environment. The script compiles the Fortran program using the Cray Intel Fortran compiler with the FOpenMP and O3 options together with the qopt-matmul option. Unlike the NRIS Intel compiler, which required the X-host option, the Cray Intel compiler automatically applies CPU-specific optimization through loading of the AMD Turin module, which was done above. After exiting the job script, I will return to the terminal and clear it. I will execute the Fortran program by submitting the job script to the Slurm queue system using the sbatch command. We can see that the job is assigned the number 4266. Using the slurm queue command, we can see that the job has been computing for 15 seconds on the C199 node. I will use the more command to open the slurm job output file. The job output file first shows the list of the module used. The matrix multiplication using Cray Intel was completed in about 15 seconds with 256 CPU cores. The job output file shows that the CPU efficiency was about 59% and the memory usage was about 25 gigabytes. I will now perform a scaling analysis, but first, let me clear the terminal. To begin, I will list the contents of my folder. I will use the Python script named setup testing OpenMP to conduct the scaling test. The script uses the OS module to execute Linux commands and was previously reviewed in video 44. The scaling test also uses the script named testing OpenMP, as in our previous videos. This script will not compile the Fortran program, but use the executable I just generated in this video, using the mxm OpenMP job script. We can take a look on this testing script. The only difference between this script and the one used in video 45 is that I am using the Cray Intel programming environment instead of Intel loaded through the NRIS module system. After exiting the Emacs editor, I will clear the terminal. I have the Python module in my home environment, as explained in video 44, and will begin the scaling analysis by executing the Python script. The terminal displays the sbatch commands executed by the script. Applying the show queue command confirms that all my jobs have started. Before checking the results, I will clear the terminal. I will first list the content of my folder with the ls command. I use the more command to look at the last slurm output file. From this file, we can see that the module load commands in the job script has switched to the Cray Intel programming environment. We can also see that using 256 threads results in a wall time of approximately 14 seconds. The job output file shows that the CPU efficiency was about 75% and the memory usage was about 25 gigabytes. I used the data from these scaling tests to create figures showing the wall time and CPU time. The figure displays the wall time and CPU time with a logarithmic scale on both axes. Let me first enter the number of threads or cores used in the scaling analysis. I can add the mean wall times to the figure. I will enter the CPU times calculated by multiplying the wall times by the number of cores used. Finally, I include the speedup factors between tests. The reason for plotting the CPU time is that this curve would form a straight line if the scaling analysis had shown a perfect speedup factor of 2 for all tests. We observe a near-perfect speedup up to 16 cores. The scaling analysis shows that a computation taking about 1,205 seconds on a single core is reduced to approximately 80.3 seconds on 16 cores, achieving a speedup of around 15. In an ideal scenario with perfect speedup, this would have been 16. The speedup decreases when scaling from 16 to 64 cores. The scaling analysis indicates that a computation taking approximately 80.3 seconds on 16 cores is reduced to about 24.6 seconds on 64 cores, achieving a speedup of roughly 3.3. In an ideal case with perfect speedup, this would have been 4. The speedup decreases further when scaling to 256 cores. The scaling analysis reveals that a computation taking 24.6 seconds on 64 cores is reduced to approximately 14.3 seconds on 256 cores, achieving a speedup of about 1.7 instead of the ideal speedup of 4. The scaling analysis shows that a computation requiring 1,205 seconds on a single core is reduced to about 14.3 seconds on 256 cores, resulting in a speedup of approximately 84, which falls significantly short of the perfect speedup of 256. A perfect speedup is unattainable because, as explained in video 11, there will always be sections of a program that cannot execute in parallel. These sequential sections increasingly limit the speedup factor as the number of cores used for parallel computing grows. As observed in these scaling analyses, there is near-perfect speedup up to 16 cores, but this diminishes when scaling to 32 and 64 cores. The speedup factor declines even further when utilizing 128 and 256 cores. In the next video, we will once again use the Intel Fortran compiler loaded through the Cray module system. However, instead of the triple-nested loop used in this video, we will utilize the MKL routine. I am looking forward to the next video, wishing you all happy computing in the meantime.